So, I want to talk to you about the correspondence between, let's just say R3 and the wedge product. And I'll also introduce the hodge dual map, although that may be premature on my part, but I'm going to do it anyway. So the essential idea here is that, and I'm just going to go ahead and take the wedge product of vectors for the purpose of this part of the course, because it's just kind of more natural in some sense or another. Oh, maybe I shouldn't do that. Golly. Fine, I won't. All right, so start with, I have omega is a mapping from, let's say, R3 to lambda 1. And I have phi is a mapping from R3 to lambda 2 of R3, okay? And the mapping is just this. Omega of ABC is AE1 plus BE2 plus CE3. And phi of ABC, and I'm writing the kind of like a sequence kind of notation. The input is a subscript. Okay, that's just the notation I like to use here. And here I have A, E2 wedge E3 plus B, E3 wedge E1 plus C, E1 wedge E2. So this is the so-called work form correspondence. And this is the so-called flux form correspondence. Although that terminology really belongs more properly in the next chapter, where we're actually talking about vector fields and differential form fields. Now, oftentimes when people talk about a differential form field, they just say differential form. So it's like, I mean, usually we have no trouble distinguishing between like vector field and a vector. But for differential form, just you don't hardly ever hear people talk about a differential form field, but that's usually what a differential form is. Or just a p form, for example, is usually a differential. It's usually an assignment of a p form at each point in space. You might say a p form field. All right. Anyway, this is the work form and the flux form correspondence, and the Hodge dual is simply this. Like the Hodge dual of omega of vector A is the flux form of vector A, and the Hodge dual of the flux form of vector A is the work form of vector A. And finally, the Hodge dual of the number 1 is E1 wedge E2 wedge E3, and the Hodge dual of E1 wedge E2 wedge E3 is 1. So you take these three rules and you extend linearly, although there's really nothing linear. These are already pretty much the full rule, but these ones down here extend linearly, and this gives us the Hodge dual is a mapping from p forms on R3 to 3 minus p forms on R3. See, you give it a 1 form, it spits out a 2 form. You give it a 2 form, it spits out a 1 form. You give it a 0 form, it spits out a 3 form. You give it a 3 form, it spits out a 0 form. These are the Hodge dual, and you can pretty straight away prove that Hodge dual of alpha is equal to alpha again. for all alpha in the exterior algebra of R3. So the Hodge dual is naturally a mapping on the exterior algebra. So that's Hodge dual. So we can, it's just useful to introduce that language so that we can write down formulas is all I'm saying. All right, that's all I'm really saying at the moment. How to properly define the Hodge dual in terms of something more beautiful and geometric is probably beyond this course. But I will also talk about the Hodge dual in like Minkowski space eventually. All right, so what's the deal with the work form and the flux form correspondence? Well, here's the basic calculation. If I have omega A wedge omega B, all right, that is like A1 E1 plus A2 E2 plus A3 E3, right? Wedged with B1 E1 plus B2 E2 plus B3 E3. And what do we get? Well, we get A1 B2 minus A2 B1 E1 wedge E2 plus A1 B3 minus A3 B1 E1 wedge E3 plus A2 B3 minus A3 B2 E2 wedge E3. All right, so then what? What is this? Can you recognize what's going on here? What is this? What is this guy in terms of the cross product of A and B? Can you recognize what this is? What is this in terms of the cross product of A and B? What is this in terms of the cross product of A and B? If you think back to your calculus, yeah?
That's the first coordinate.
Well, no, not the first coordinate. This is actually, remember to get the z coordinate, we take the x hat cross y hat minus y hat cross x hat terms. So this is actually 3. This is the third component. This is, yeah, this one's the first one. This one is actually minus the second one. Because if you, I mean, you can remember the signs in terms of this cross product, right? I remember it in terms of the circle of cross products, right? Like x hat cross y hat is z hat, but z hat cross x hat is y hat, and y hat cross z hat is x hat, you know? So you notice that it's like 1, 2 is 3, 2, 3 is 1 cross product, but then 3, 1 is 2. So there's an asymmetry in the formula right here for the cross product, and that is exactly why you'll notice I anticipated this and I folded that. See right here? Notice that. So this does act in slight disagreement to our convention over working with increasing indices, increasing multi-indices. Like 3, 1 is not it's not a welcome member of the, I mean, that's not an increase, 3, 1 is not an increasing multi-index of, you know, order 2. It's kind of out of place, but it's what you want to make this formula work nice. See, because what this is the flux form of the cross product. That's what's going on here. So the wedge product of 2 1 forms gives me the flux form of the cross product of the vectors to which they correspond. This is how the cross product and the wedge product are related. And then of course if you can do it twice, you might want to do it a third time. What happens when we take like a flux form wedge product with a, let's just look at that for a second. What's the deal with a flux form wedge product with a work form? All right. What happens when I take a flux form of, say, vector B, and I take the wedge with C? What's that going to be? Let's write it out. Let's work it out, right? What's that give us? So this would be, let's see here. Yeah, B1 what? E2 wedge E3 plus B2 E3 wedge E1 plus B3 E1 wedge E2 by the definition of the flux form, right? Now that I take the wedge product with, oh my bad, I shouldn't, this doesn't even make sense. What do I have to, my notation, I have to do omega sub C, my bad. Sorry about that. I'm not taking the wedge product of vectors directly. I'm not one of those people. Sorry, there's a whole field of these geometric algebra people who argue with a religious devotion that you must do everything in terms of geometric algebra. It's the only way to think, blah, 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 blah. And I'm just not a true believer in the geometric algebra. What can I tell you? Maybe someday I will, maybe someday someone will come and convert me. It just hasn't happened yet. Because, I don't know, whenever one of these folks comes around, I always ask something along the lines of, okay, so why is that better? And I never really have gotten a convincing answer. But that's just me. It does have its devotees. So there's that. And then you take the wedge product, right? But how does the wedge product work? The wedge product works so that if there's any repeat, it's 0, right? So while in principle you've got a trinomial times a trinomial, which gives you 9 possible terms, 6 of those are automatically vanishing because there's only 3 which have distinct collections of 1, 2, 3 in terms of the wedge. So like, for example, you got yourself a B1, C1, E2, wedge E3, wedge E1. No parentheses needed because the wedge product is associative. Then you got yourself like a B2, C2 of E3, wedge E1, wedge E2. Then you got yourself like a B3, C3 of E1, wedge E2, wedge E3. Aha, well, you see what we could do there. We could just write B1, C1 plus B2, C2 plus B3, C3 all times E1, wedge E2, wedge E3. Right? Why is that? So like the... Yeah, right, I have to, 2 transpositions, so minus, and then another minus is plus, and here I have to move it 2 spots over, donk, donk, so each time I move it twice, so it's a plus, and the first one, the last one's already what it needs to be. But what is that? Well, that's the dot, yeah, that's the dot product, that's B dot C, right? E1, wedge E2, wedge E3. Ah, well that's kind of cool. So that gives us another relation. That's how the dot product appears in this business. We can obtain the dot product from taking the wedge product of a flux form with a 1 form, and that's kind of weird. And but of course we can throw in Hodge duals, right? If you want a stone cold formula for the dot product, here's a really, like here's about the most complicated way I could possibly think of calculating a dot product. I'd do this. Oh well, you just take the what do you do? You take the Hodge dual of the flux form of B, wedge product with the work form of C, and there you go. That's your dot product, right? Because the flux form of E1, the Hodge dual of E1, wedge E2, wedge E3 is just 1. So there's a stupid formula for the dot product if you want one. Although it's a little bit disconcerting in a sense because you're like, but the dot product is commutative. right? So if that's true, what has to also be true here? Well, this, of course, is C dot B, right? And by the symmetry of the calculation, that has to be the Hodge dual of what? The C wedge omega B, which is a little bit disconcerting, but it's got to be true, right? And by the way, the Hodge dual is an isomorphism, so this implies that the flux form of B, wedge product with the work form of C, is equal to the flux form of C, wedge product with the work form of B. And by the way, I don't think I've ever derived this before. I think this is new for you today. I feel like this is a decent homework problem for some other course. This would have been a good homework problem for your course if I'd thought of it before I shared it with you. My bad. In fact, I'm probably obliterating various homework problems as we speak, but that's okay. Any questions? So the larger question I'm asking is, in Calculus 3, we have vector fields. We do things with them, right? Or you can think about vectors at a point, and we basically have a dot product with a cross product, right? How can we recover those concepts here in the language of wedge products? Well, we've seen both now. One other thing we could do would be like the triple wedge product, right? Like what would omega A, wedge omega B, wedge omega C look like? So that's going to be what? That's like the flux form, A cross B, wedge with the work form of C, which is right. And then of course, what do you get? You get your E1, wedge E2, wedge E3, right? But that also is the determinant of A, B, C, E1, wedge E2, wedge E3. This is the so-called triple product from Calculus 3. And this has to be the case, you see, because there is a unique, here's a theorem, there's a unique completely alternating n form on Rn which sends the identity to 1. Let me write that theorem down. Theorem. There exists unique alpha in lambda n Rn such that alpha of E1, E2, da 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 En is equal to 1. So if you want to look at that, another way you could look at that, if you have an n form on En, you can think about it as a function of matrices. So you could think about that really as alpha of the identity matrix equals to 1. If you'll allow me that abusive notation, we're identifying, like alpha of A is equal to alpha of like the first column in A, the second column in A, the nth column in A for that n form, that notation. But the completely anti-symmetrized type n0 tensor on Rn, which sends the identity matrix to 1, is the determinant. That's not quite accurate. It's what? So like you can prove if you've got alpha of, say, V1, V2, Vn, well, that's equal to the determinant of the matrix, which you get from just putting those as columns, times E1. Oh, my bad. Well, that is equal to that, but my point is that's also equal to E1 wedge E2 wedge wedge En acting on V1, V2. That's what I'm trying to say. So with this correspondence in mind, the determinant is, as a n-linear map, the determinant is the wedge product of E1 with E2 all the way out through En. Now there's a prop. Now I think there's a better. I may have another definition for determinant other than that. Let me see here. Oh. So one very interesting homework problem from all this is advertisement, right? You can prove the determinant of A times B is the determinant of A, determinant of B in this world of thinking, and the proof is actually not too horrible once you understand it correctly. Now, so I think I usually defined the determinant implicitly here, but I kind of like that I have an explicit. I haven't tried this. I don't know if I've ever written this down before, Ernesto, but I do think that this is not an unreasonable definition. The determinant is equal to E1 wedge E2 wedge wedge E3 En, right? With the notation in mind. I think that might be a very nice way to derive this. The way I have done it before, though, it usually filters through. I'm not signing up for this until I've worked it out. I've gotten tricked on this before, but the other, of course, the usual definition I give is this, which is just that like V1 wedge V2 wedge wedge Vn is equal to the determinant of V1 V2 Vn with E1 wedge E2 wedge wedge En. That implicitly defines the determinant of that matrix. We can use that to implicitly define the determinant. You can start to see it works correctly. First of all, it's completely like, of course, this is completely antisymmetric in any exchange of columns, right? Completely antisymmetric in any exchange. This, of course, is completely antisymmetric. You know, the determinants like that. Yeah. What else? If I have any, if I have any repeated column, I get 0. If I have E1 wedge all the way out through En, that would be the identity matrix. the determinant identity matrix is 1. This formula reduces to E1, wedge E2. There's lots of circumstantial evidence for this being the right implicit definition, but man, I actually really like this, that I just thought of this way of writing it. It's just, that's an explicit definition for the determinant in terms of the wedge product. I just have to be willing to embrace the notation that I'm going to say the determinant, an n form acting on a matrix is the n form acting on the columns of the matrix. Is that the meaning here? I'll let you work on that homework. That's definitely one of the homework problems you should try to do. You should try to do this. Do you remember proving that in Math 321 or 221?
Not sure.
See,
Probably.
because the proof of the determinant of the product is a product of the determinants, the proof is actually pretty hard in the regular way of doing things. Like, you have to descend to elementary matrix arguments, and you have like a singular, when the matrix is singular, it goes one way. If you have a non-singular matrix, you have a different argument. It's a mess. Like, it takes a while to actually prove that in terms of the, first you prove that the identity is true for any pair of elementary matrices, and then because that's true, and any invertible matrix can be written as the product of elementary matrices, then you get the identity for two invertible matrices. But then if one or the other of the matrices is degenerate, if it's singular, then you can prove the determinant of both sides have to be 0, because the product of a singular matrix and anything else is singular. You can prove that.
I feel like we might have proven that in 421. But
421. Oh, wow.
I'm not sure.
That, I would be shocked if you proved that. If you proved this in 421,
Maybe.
I will pay you $20. Because this is linear algebra proper, which Dr. Sprano has a well-documented hatred for. Well, maybe not. Maybe this is the part which would be okay, because it's not just. I have my doubts. But anyway, okay. So that's the wedge product, and of course, once we talk about chapter 10, once we talk about calculus, then this comes to new life, because then we'll see a connection between like the gradient, the curl, and the divergence, and what we'll call the exterior derivative. So we'll come back to this then. But this is the algebra of it. And so a natural question is people always ask, is the wedge product the cross product? The answer is no. It's not. It's related to it, but it's not it. And then the question is it a generalization of the cross product? Well, depends on what you mean by generalization. Like, how would you define the cross product in n dimensions? If you had to, Ernesto, what would you say about it? First of all,
in R3, the cross product is the orthogonal vector to two other vectors.
Ah, right.
So it would be something like if we have n minus 1 orthogonal vectors, then the cross product of those n minus 1 vectors is like the n orthogonal vector.
Ah, so that's kind of the two different ways. It's like, given V1 and V2, find V3 in the perp, right?
Mm-hmm.
Or is it given V1, V2, Vn minus 1, find Vn in the perp of all those? So, this is of course not this is some sort of tertiary or n minus 1 array product, right?
Yeah.
There is, this is a thing, and in fact, yes, you can define Vn as the determinant of x hat 1, x hat 2, x hat n, V1, V2, Vn minus 1. Like, that is, in fact, a formula. And if this is, if you're a, if you're a high and mighty mathematician and you refuse me that formula, well, fine. Here's a well-defined formula: I1, I2, da da, IN, V, VI1, VI2, da da, VIN. My bad. -1, x hat sub n. There you go. This is just that formula. Or if you don't like that, you could say it's the Hodge dual, suitably extended meaningfully. V1 wedge, V2 wedge, dot wedge. Vn -1, I think. I'm not sure about that. Actually, I shouldn't write that. I'm not sure about that at all. That's just a wild conjecture on my part at the moment. Let me erase that. That should be a homework problem, at most. Or it's just not true. But yeah, this is a generalization of the cross product, right? But yeah, it's definitely not unique, right? Like in 4 dimensions, if I've got, 1, 0, 0, 0, and I've got, 0, 1, 0, 0, well, if I want vectors that are perpendicular to those two, there's a whole plane, right? And like the plane, I can span it by 0, 0, 1, 0, and 0, 0, 0, 1. So there's not a unique choice. I mean, so perhaps the natural thing to say is like the cross product should be some sort of like, it shouldn't be an object of the same type. Maybe it should be, if we think of the original ones as 1 vectors, maybe the perpendicular thing is like a 2 vector or something. These are the kinds of ideas we would investigate. But anyway, my brother actually wrote a paper that has this in it and discussions of the history of generalizations of the cross product and things. So a few years ago. He actually gave a talk about it here a while ago. All right, so moving on. Let's talk more about the musical morphism. All right. So I also have a discussion of like the Hodge dual and the wedge product in 4 dimensions in the notes. So I'm gonna skip over that for the moment. I'll come back to it once we've got chapter 10 stuff. I'll do it then. Do it all together. Okay. But yeah.
It's a musical morphisms in chapter 9.
Yeah, but not. I don't think the notes on the musical morphisms are quite complete. Let me try to talk about what I'm talking about. All right, so if the musical morphisms, it's just a stupid pun like everything else. Let me try to talk about it. All right, so suppose we've got V is an inner product space, or I don't even need to say that much. Well, a geometry. So a geometry meaning that it's a vector, V has dimension, for me, a vector space of n dimensions over the reals, and G is a mapping from V cross V to the reals such that G is bilinear, symmetric, non-degenerate. So that's not an inner product. That's like weaker than an inner product because it doesn't suppose, like the inner product has a positive definite condition that like G of x comma x is necessarily non-negative. Excuse me, the G of x comma x is positive if x is equal to 0, if x is not equal to 0. I make no such restriction here. To say it's a metric, so this in physics, This is typically called a metric, which is, that's physics language, admittedly. Like a metric in mathematics does not, it's not this, like a metric in metric space would not comport with this usage of the word metric.
Because metric has to.
Right, yeah, I mean, so the basic example that you always run up against, whatever example I'm on, I don't even know. Let's call it 4. If we had G on R4, you could do this, like G of xy is equal to x transpose minus 1, 1, 1, 1, y. All right. So this is the so-called eta matrix. Zeros on everywhere else, right? So if you have this as your, and you can easily check that this is bilinear, check, symmetric, check, non-degenerate. Well, non-degenerate just boils down to the determinant of the matrix of G is not equal to 0. Okay, so the determinant of this matrix is equal to -1, so we're fine there.
Is that what non-degenerate means?
Yeah. I mean, you could give a more basic definition in terms of, it means that if G of x comma y is equal to 0 for all y in V, that implies that x is equal to 0. Which, if you look at that in terms of the matrix of G, that boils down to what? That boils down to the only, if you look at the matrix for G, the only 0 solution to it is the homogeneous solution. So, yeah, anyway. Okay, so this is a metric, quote unquote, and it has null vectors. See, if I put x equals to y equals to, for instance, 1, 1, 1, 1, like that, then notice that, we call this not, notice that g of x naught is equal to -1. Oh, my bad. That was too much. I need to throw some zeros into the mix. There we go. So then it's -1 plus 1, also known as 0. Woohoo! That's weird. That's weird, right? That's not an inner product. You don't have non-zero vectors having an inner product of 0. This is foreign to our experience in linear algebra, for sure. Dr. Skambordis loves inner product very much from the very core of his being, but you will not see him giving this as an example of an inner product because he knows what an inner product is, and this is not one. And it does come at great cost. The theory which is known for inner products is beautiful and simple. The theory for metrics, still beautiful, but not so simple. But many things are known. All right, anyway. So, my larger point to you is this. If we're in a geometry, which is a vector space paired with a metric, okay, a geometry is a vector space paired with a metric, we can use the metric to, and so I should make a definition here. Definition, Gij equals to G of Ei, Ej, right? And G upper Ij times G J lower k is Kronecker delta Ik. In other words, the matrix G upper Ij is equal to the matrix G lower Ij inverse. So the metric, the metric components written up is not a metric. It's actually the inverse matrix to the metric is the definition here.
G upper Ij are the Ij components.
Yeah. So this right here is this defines G upper Ij, and I'm missing a sum. Sorry, my bad. It's my Einstein summation notation showing through. My bad. I do try to not do that in here. The Einstein convention is that repeated up-down indices are summed over, but I do put the sums in. So does that answer it?
But what's the difference between upper Ij and lower JK?
Well, lower Ij is just the components of the metric, and this This comports, this is exactly the definition we gave before for bilinear form, of which this is one. The gi upper ij is not the components of a bilinear form. It's the inverse to g as a metric. It may or may not actually be the components of a corresponding bilinear form. I mean, I guess you could make a bilinear form, but we don't think about that. So I don't think about that at the moment. All right, so what to do with this? See, well, let's see if I can show you. All right, let's see if I can get this right. So, construction. Grief. Sometimes I wonder if this is a school. It's just a giant Christian camp. It's not actually a university, I think, sometimes. I don't know. Do I need to edit this video now? No, it was set out of love. It was set out of love. All right, so, I mean, I did come back, didn't I? All right, so construction. I want to show you, given, let's say, V in V, we construct I want to say flat. Man, how do you make the flat symbol? How do you draw like the musical flat? Is that what it looks like? That's not it, is it? Like, what's the flat in music look like? Is it? Let me Google. Show me a flat in music. There we go. That's the symbol I'm looking for. The flat is blah, blah, blah. All right, flat of V. All right. So remember, V is equal to what? V is equal to a sum I of V upper I, E lower I by our notational rules, right? So beta, the flat, we do a sum over J of G, sum over I and J. I want to say G, I, J, V upper J, E upper I. Yes. So you see what I did here? And then this right here is it defines V lower I is equal to definition. The sum is over the, I gotta, well, I only need one of the summations, not both of them. Okay, so let me just say down here. VI is the sum over J of GIJ V upper J. This is what the musical morphism looks like at the component level. In the old physics language, these are the covariant components of vector. These are the contravariant components of a vector. In this viewpoint, physicists are like, well, you can either treat a vector as a contravariant thing or as a covariant thing. If you got a metric around, you can switch from one to the other, and they're isomorphic, so what does it matter, you know? I'm not sure if physicists actually say that, but that's what they do. They raise and lower indices. I asked my special relativity instructor what raising and lowering indices was. He's like, well, I was like, how do you lower the index? And he's like, you just you contract, which is what this is. This is a contraction. You just multiply by the metric, and you sum over, sum over over the contravariant components, and that's the covariant components. And we were like, yes, but why is that how you lower indices? And I think after about the third or fourth time we asked him this question and he gave us the same answer back, he's like, you know, there's a guy in the math department who likes to think about these things, and you should go talk to him. And that is how I met my advisor, actually. That is the question which led me to Dr. Fulp. And then I went to Dr. Fulp and I was like, what is a tensor? Because that's really the more basic question I was asking. And Dr. Fulp was like, what kind? And I was like, now I'm in the right office, you know? That's the right answer. What kind of tensor are you talking? There are many different kinds of tensors. All different kinds of tensors respect different kinds of coordinate change. All right, so, but anyway, that is the flat. So you're taking a vector and you're making a one form. See, this is an element of V-dual. However, you can do the other thing. Given alpha in V-dual, you can construct, now I gotta look this up, symbol for sharp in music. There we go. It's like a slightly italicized hashtag or something, you know? So the sharp of alpha is equal to the sum over I and j. And now we use not the metric, but the inverse metric, g upper ij, alpha lower I. And then I would do e lower j. That right there would be an element of V. And the reason it's a flat and a sharp, it's really a dumb joke, okay? You see this? So like alpha upper I is equal to a sum over j of g upper ij alpha j. See that? That's definition here. Do you understand why it's a sharp and a flat? So in music, if you go just the next, if you go up, it's like the sharp. So it's going up. The index is, it's an index raising. In the flat, we're lowering the index. That's the stupid, that's why they're the musical morphisms.
So this has nothing to do with music.
Yeah, no, it has absolutely nothing to do with music whatsoever. Well, at the levels of my current creativity, it has nothing to do, but I'm sure you could find a way to extend the pun, you know. The pun could be extended, I'm sure there's a way. So this, you see, once you have the metric in a geometry, we can take a tensor of type RS and we can convert it to a different kind of tensor by systematically using the idea of the musical morphism. Like, let me show you a really different example. Now this becomes more the inverse metric becomes more interesting in later contexts when the metric has a coordinate dependence. See, eventually the metric would be at each point it has these properties, but it can vary from point to point. And the dependence of the metric on the point underlies the geometry of the space which we're modeling. Now at the moment I'm just talking about the geometry of a vector space, which is kind of boring because it's a flat space, whatever. But if you're talking about a curved space and you're talking about a metric, really a metric tensor field, it can have a coordinate dependence, and then the inverse metric will also have a coordinate dependence, and you get all kinds of interesting formulas entering in like these things. And like this can be used to derive the coordinate formulas for like divergence and curl and other coordinate systems and things like that. Anyway, let me focus here. So for example, if I had, say, T is a mapping from V cross V cross V dual to the reals, where V is a geometry, right? Then this is T equal to what? Something like a sum of T, how's it go? Oh man, is it lower IJ, upper K? Yeah, I think that's how it goes. And then I have like EI, tensor EJ, tensor E lower K, right? Is that my notation? Oh, yowzers, bowsers. Let me flip back for a second here. It's been just long enough I've forgotten our notation. So type RS. Type RS. Yeah, that would be a type 2-1, right? Okay. So,
Although isn't that technically backward? Then we start with the vectors. Well, and then the duals.
yes, but I'm not talking, I'm building the tensor, or not, it's, this is it mirrors that. You know, if there's vectors here, there's dual vectors here. The dual is acted on by the double dual. All right, so in this context, you could do things like talk about T, for example, Tij lower k, and that would be equal to summation, all right, over k of what? Well, of not some, I need some over some other letter, some over L, let's say, of G K L T I J K, like that. And so the kind of annoying thing is that it's customary to use the same letter for here and here, but technically speaking, you're really defining a new tensor. See, I mean, we're really defining S is a type 3-0 tensor, right? And I think I can write the formula for you. What is S of x, y, z equal to? Good grief. Bunch of hooligans. I think I can do it. It's, I could be wrong about this, but let's try it out. It should be T of x, y. That stays the same, right? But what's the, I bet, and I'm just conjecturing here, Ernesto, but I bet it's got to be, I want to convert z into a, what does t act on? T acts on pairs of vectors with a dual vector, right? So if I want to convert a vector to a dual vector, I do one of those guys, right? And well, okay, anyway, so that would be the sum over I, J, K, L of x upper I, y upper j, And let's see here. Let me just do sum over I and j. Sum over I and j. And then the sum over, let's see here. Let me just say sum over k of g, g, oh good grief, L, K, Z, well, I guess I got to do K and L. Z, K, and then I've got my T of EI, EJ, and E upper K, E upper L in my current. So what I did was I just plugged in the formula for the flat into that, and then I pulled out the sum and changed the letters so they don't overlap with the other existing letters, and fine. So you've got, you know, sum over I, J, K of xi, yj, zk, sum over L of g, L, K, T, I, J, upper L. And that, whatever goes right there, should be the meaning. I mean, that has to be what is the SI, IJK. That's what that is. And I think that's what I claimed, quote unquote, TIJK would be, right? It's just like the contraction with, yeah. Listen, I'm being a little bit careless about which index of G it's summed over because G is symmetric, so it doesn't really matter whether I sum over the first or the second index because it's symmetric. I can be careless about that, and I am being careless about that. If you were in the context where your symmetric was not, where your metric was not symmetric, well then, technically speaking, it wouldn't be a metric as I've defined it today. But then you'd have to be careful. However, there is a context where there is something that you might think of as just like you might ask, well, can you talk about a metric which is bilinear, symmetric, or anti-symmetric and non-degenerate? Anti-symmetric meaning that, you know, g of x, y is equal to g of minus yx, and the answer is yes. In fact, symplectic geometry is based on such a metric. So there's a lot more to say about this if you were to have a really good abstract linear algebra course. If you want to read more about these things from a really abstract and pretty good perspective, Roman's Advanced Linear Algebra, I think it is a pretty good place to read. He also has a YouTube series on category theory, which I have not watched, but it's probably good. I think he's retired, but he wrote some really nice books. He has another book on umbral calculus, which I don't know what that is either. Anyway, that's all for today. So.